first, a little bit about our history. So our team was actually founded in 2012. It broke off off of another design team that's here on campus, UBC Aero Design. And after it broke off, it actually went back into Aero Design in 2013. So they spent a year on their own, they went back in, and then they decided to merge out again. And then that year, which was 2014, so ever since the 2014-15 year, we've actually been our own standalone independent team. And that year we actually placed 5th at our national competition and received an innovation award. Ever since then, we had a long run of successful competitions, placing 5th 2 more times, and then placing 3rd place in nationals, and participating in or attending the international competition as observers. So we actually had an aircraft lined up to go. We had an unfortunate crash, but we managed to get an overall look at the competition. And then from there, we actually participated in it for the first time just this past year in 2019 and managed to place in the top 3 Canadian teams internationally. So now I'll pass it off to Eureka, who will talk a little about our recent accomplishments.
These are some of our past accomplishments. Here's Desert Hawk, that's our fixed wing project from 2017. This is the project that Adam was just talking about, which crashed a week before competition, unfortunately. But we've got some more projects. We've got Raven over here. This was fully carbon fiber frame, booms, as well as propellers. The idea behind Raven was it was supposed to be a network relay, so all of our communications could be extended to a longer range. Speaking of range, we've got our antenna mast that we previously have been using. We host all of our communication systems on top of the mast to affect ground effect and for our range. As well, last year's legacy aircraft, you'll see Condor in front of you right here. Condor can go as fast as 100 kilometers an hour. It's pretty crazy. It runs on about 8 to 9 horsepower, and we did place top 2 Canadian at our international competition with this aircraft. Okay.
So yeah, now going forward off of those projects, so now with projects such as Desert Hawk and Raven, we learned a lot. That was in VTOLs, into quadcopters, so now we especially focus on quadcopters because we do find that they can be best for our competition, as you'll see in our aircraft presentation. But building off of that knowledge, we went ahead with our 2019-2020 project. So as I said, we have our 4 sub-teams. Radio communications, which focuses on our antenna tracker. This is a device that allows us to use directional antennas to enhance our long-range video and image transfer. We also have our ground control software suite. It handles most of our image processing, connecting to the competition server, and basically glues the entire system together. We have our aircraft. So this year we'll be building brand new aircraft named Kestrel, and this is to hopefully achieve the greater range requirements presented by our competition. And on our payload systems, we'll be focusing on specing a lighter camera, having a successful rover airdrop, and as well, that includes the winch, so the entire airdropping mechanism. And as well, we're going to be doing all that with our onboard computer.
We've got 2 very exciting competitions that we go to every year. We've got our Unmanned Systems Canada competition. This is the national one, and we compete against 14 teams every year. This year, the scenario is really interesting. It's a medical emergency in the rural communities of Manitoba. So the idea is the ground between the delivery location and the clinic is inaccessible by land, and so we want to deliver these medical packages. We've also got UBC, which is our international competition. We've got another air delivery scenario in here. We're gonna perform 3 components in this competition. I'll talk about them in a second. But the focus in AUVSI is basically, the focus here is on systems engineering and automation. So the idea is at the start of your mission, you're going to press one button and everything needs to be automated, and the whole system just needs to finish the mission by itself and successfully deliver the package. So for both of these competitions, we begin by doing strategy sessions within the team. If you could pull up the strategy. So we make spreadsheets, and basically we strategize where we want to maximize our points because these are actual challenges and it's actually pretty hard to get 100% of the mission tasks completed. So we'll play around with figures. ABSI has 4 major components. One is autonomous flight. So we grab waypoints from the interop server that the competition provides us, and we need to fly that waypoint path. The next one is obstacle avoidance. This same interop server gives us static obstacles. Sorry about that. This year we've also got dynamic obstacles, which means there's other aircrafts we need to be looking out for. So that makes the competition a lot more harder this year. We've got ODLC, which is object detection. So there will be letters on the ground, and our aircraft needs to identify the characteristics such as color, what letter it is, geotag them with the location and time. So that's worth 30% of our mission. And lastly, we've got an airdrop component. So we're gonna have an unmanned ground vehicle, a rover attached to the bottom of the drone. The drone's gonna fly to a specific location, deploy the rover, and the rover is gonna drive up to the actual delivery location. So again, for USC as well, we do the same thing. We look at where we wanna maximize our points, where we wanna achieve autonomy, and where we wanna do tasks manually. Of course, our aircraft team and payload team will talk about that shortly.
Awesome, thank you, Karika. So a lot of our projects that I spoke about earlier are drawn from the competition requirements that Karika just mentioned. However, with that, we encounter several design challenges within these subteams. So first, focusing on communications, antenna tracking it enhances our radio communication. However, radio communication in itself can be a little unreliable at times, so it can be really tricky to work with. And in fact, it's the most common component to fail amongst teams at competition. Luckily, we were able to create our first fully functional antenna tracker last year, so we're building off of that this year. However, it still proves to be quite the challenge. With our ground control software suite, one of the biggest challenges we face is ensuring appropriate cohesion throughout the entire system and making sure that everything's integrated properly. And this can be countered through a lot of mission testing that we do. On our aircraft team, as Karika mentioned, we have waypoint flights, which have longer ranges. This year actually increased by about 50%. So in that sense, reaching those longer ranges and being able to provide the appropriate power and propulsion to get there can be relatively difficult. As well, getting there isn't just a problem because we also have to get there with our large payload capacities for completing the other tasks. And on the payload side, they can do their job best by helping the aircraft make, the aircraft team and make their lives easier. So their design challenges focus on making sure that the rover and their airdrop mechanisms are small and light. As well, like I said last year, our camera was a little bit too heavy. So by speccing smaller cameras, this can help us help the payload team, and this can be a challenge for them as well. So now I'll pass it off to Eric, who will talk a little bit about our system integration.
Yeah, so I'm just gonna give a brief little overview. Here is actually a stripped down version of our system map, and it's just all the little blocks of software that hold our system together, as well as their accompanying hardware components. So all the blocks in blue are pieces of software that we here at UAS create, and the non-blue blocks are either hardware or third-party software that we use. So you can see up here is the most important thing. It's our flight controller. This is the brains of the aircraft, and we communicate through that through a proxy that we made called Skylink. So it acts as sort of like a proxy / translation service, and it allows us to get telemetry information from the flight controller, which is used by the antenna tracker to track its location, as well as in our ground control suite. So our ground control suite is just a web server application that presents us with a few UIs and acts as sort of the central hub of communication between us, the team, our system, and the competition servers that we connect to. We also have all sorts of other utilities called SkyPasta is what takes triggers the camera, takes the images, tags them with their information, and serves it to the ground. We have air command, which allows us to remotely control and guide the aircraft, in addition to what the autopilot already provides, and all sorts of other various telemetry and avoidance utilities. And the big theme this year was redundancy. So in the past, we've had communication failures, and since telemetry is such an important part of our system, it scores us points, it lets us know where the aircraft is and make sure that it's safe. We've gone for 2 radio links, so they run on different frequencies, they run on different technologies, but anything that uses telemetry can aggregate from both links so that we always have a fail-safe.
Thank you, Eric. So with that, that sort of concludes our introduction. I hope that gave you a brief overlook of what UAS is, who we are, and sort of our competitions and what our focus is, as well as a little bit of an introduction on our system. So now, just before we hear from Oliver and our aircraft team, are there any questions I can answer? Yeah.
All the students of UBC can participate? Like, is it like, yeah. What if you graduate? You just drop out in the team?
Well, yeah, so we are allowed, so on our team, we're allowed unlimited undergraduate students to participate, and then we are also allowed 1 graduate student. But technically, yeah, everyone on the team is a student at UBC from any faculty, so it could be business, arts, or applied science makes up the bulk of our team. Awesome, so I'd like to welcome Oliver and our aircraft team, and they'll go ahead and talk about our aircraft team for this year.
And all the UAS members here. I'm Oliver, and I'm the aircraft lead this year, and these are my colleagues. I have Sean, Matterjot, Nick, Grant, and Sahil here. So this is a brief overview of what we're going to be doing today. I'm going to start with a little bit more in depth about our challenges and specific problems we're going to be facing this year. And then I'm going to go into more of our detailed design. We'll have our team members introduce each of the parts that they're working on. And then we will also go into some closing. We can summarize the challenge we're facing and get some questions and feedback. So for you guys members, you just want to just take out your phones and just scan that. If not, I'm sure we can put a link in Slack as well. But yeah, just you can write some feedback. And then for our guests, you can just write some notes if you need. Okay, great. So our challenge at UBSI, as Adam and Karika introduced, this is going to be our main focus for this team this year. So a big challenge doesn't have to be fully autonomous. It has to be, as I said, a kind of a press go, and then it has to fly the whole route to the whole mission by itself. And we lose points each time we assume manual control. There's a 30-minute time limit for the entire mission, and that's from takeoff to landing, from the moment we lose control to the moment it lands again. And so there's 3 main tasks we have to complete, which is the waypoint flight, the object search, and the airdrop. So for the first stage of the competition, which is the waypoint flight, this is a 6-mile waypoint path, or up to 6-mile waypoint path, and this is a 50% increase over our flight path last year, which was 4 miles. And we're targeting 15 minutes this year to complete our waypoints, so we have enough time for the second 2 stages of the competition, which are the object search and drop. And we must complete the waypoints in order to progress. We can't skip over these, and once you've done this, we'll have more time to complete the rest of the sections. So for the second stage, there's an object search. So we have a camera attached to our drone, and that's going to be looking for up to 20 objects, and there's 2 different types. One of them being a standard object, as you can see there, kind of a bright painted letter, and the other one's kind of an emergent object, which could be, which is typically like a person doing an activity of interest, so have some down in the field. And then one of them is also located outside of the fly zone, so we have to have our camera be able to reach outside the scope of where we're allowed to fly. And then we have to get the GPS location of each object and a picture, and to submit that through that interop server to the competition. So in the third stage is our rover airdrop, and so this is a section where we have to deploy a unmanned ground vehicle, or a UGV, from 100 feet above the ground. This is the lowest we're allowed to fly, and for full point we have to get it within 40 feet of the drop site, target drop site. And then once the ground vehicle is on the ground, it has to navigate to a different location. And this is to simulate a stranded hiker being firebombed. Emily will discuss this more in her presentation. So this is a rough overview of the mission scoring breakdown, as you can see here. So there's a lot of points to the object classification of the airdrop, and there's a few sort of things there as well. And then, like Adam and Greg touched on, there's the obstacles you have to avoid prior to the interop server, which are both stationary and moving. You have to work to avoid. So from these competition requirements, we developed our own requirements. So we need an 8-mile range. This gives us a 6 miles to complete the waypoints and 2 for the airdrop and object detection. Our focus this year is going to be on maximizing the energy efficiency. And so we're going to be doing this through the selection of our power system. We're going to make it more efficient by using a aerodynamic shroud, which should reduce our drag coefficient. And we're integrating the payload into our frame, and this is going to reduce our aerodynamic cross-section. We're aiming for a strong and robust frame, and we need booms that are light but also rigid to minimize vibration and provide predictable behavior for the flight controller. And then finally, we need to minimize our costs, given that we're operating on a tight budget. So this is a timeline for the year, roughly. Starting in September, we worked on selecting the main components of the drone. Then through October, we're working on the general design, deciding the frame type, landing gear, etc. Then now through November, we've been working on the more detailed design. This is the CAD of all the frame, the landing gear, etc. as my team members will discuss shortly. And then coming to December and January, we're going to be manufacturing, doing the first assembly and flight tests. Then in February, it's going to be the team integration. So this is integration with the payload, the radio communications team, and software team. And we're going to be working on our shroud that's going to provide that aerodynamic shape. And then we're going to be doing mission tests. So that's starting to run the full mission tests, because often we found that a lot of our problems start to arise when we try to integrate all these different systems. And in March, we're going to do more mission testing, integrating that shroud, and then roster competition in June. So now I'll pass it off to Nick, who's going to talk about our drone components.
So before we start discussing how we chose our components for our drone, we just wanted to provide a quick overview of the different components that make up a typical drone that we would use. So here, one of the main components is the flight controller. So the flight controller is over here on Condor. It's right in the middle of these two batteries. But the flight controller acts as the brain of the operation. So it inputs, it takes in all the sensor data from the GPS, the gyro, accelerometer, magnetometer, and it outputs data that is sent to the motor and thus the propeller. And for not only does the flight controller take in the input, but additionally, it also sends data to the ESC, which is the electronic speed controller. The electronic speed controller takes in the data from the flight controller, as well as the power from the battery, and it regulates the speed of the motor. We also have the power distribution board, which is used to lower the battery voltage, since the battery that we choose is quite large and thus has a large voltage as well. And the power distribution board steps down the voltage so that different smaller components can take in the voltage to be used for telemetry, to be used for telemetry, data control, analysis. And finally, for our drone, we also have the different mechanical components. So the mechanical components are mainly the frame, which form the basis of the drone. We also have the landing gear, as you can see on Condor over there. We have the landing gear, and we have the booms that extend outward from the main frame to the different motors. So this is our new drone, Kestrel, that we will be dating this year. As you can see, there are many similarities that are comparable to Condor. And this is because Condor was very successful in quite a few aspects that we wanted to create with the new drone. And so some of the components that we tweaked will be talked about shortly by my different colleagues.
So I'll be talking about the different drone configurations we considered. So we looked at two of the most popular drone configurations, quadcopter, which has 4 motors and 4 propellers, and a hexacopter with 6 motors and propellers. So first off, quadcopter, because it has only 4 motors with 4 propellers, it's cheaper to build and much lighter due to it not having as many components. And also, because it has higher disk loading, it is more energy efficient. Next up, hexcopter, with the increased number of propellers, it is able to reach higher speeds, and it can also lose 1 motor and still keep flying, giving us some redundancy, and it's more stable.
So the software we chose to analyze all the different configurations is eCalc. So eCalc provides a friendly interface where you can enter all the different types of components, for example, the battery cell size, different configurations, the motor controller, the motor itself, the propeller, and what it does, it gives a crude estimate of our flight time, the different temperatures, and the specific load that it can support. So if we take a look at the graph, so here is the result graph from eCalc. So as you can see, remembering that our drone requirements has a flight time of around 8 miles. There are 2 lines of interest here. One is the range with no drag, and one is the range including standard drag. So eCalc provides a very crude estimate of the range of the drag. The drag coefficient is assuming that the entire airframe is exposed and not aerodynamic, and therefore you can still see that even with the non-aerodynamic airframe, we are able to reach a range of 8 miles given an average speed of 15 kilometers. We also plan on implementing a shroud in order to increase the efficiency and hopefully bring that great shot.
So when building the drone, there are a lot of variables to keep in mind. One of them is the different types of propellers you can use. So we broke them down into 3 categories: diameter, pitch, and the number of blades for the propeller. So at a constant speed, these are the benefits each type of propeller gives us. So if we increase the diameter, it will give us an increase in thrust because there's more of the lifting surface, and because of the higher aspect ratio of the lifting surface, it will reduce the induced drag and will increase the efficiency. However, rotating that propeller, that blade, will require more torque, thus increasing the power consumption. Next up, we look at pitch. So if we increase the pitch, it increases the thrust that propeller gives us at higher speeds, but it also decreases the efficiency of the propeller. And finally, if we increase the number of blades on the propellers, it gives us more thrust. However, it does so at a decrease in efficiency because each blade makes turbulent air for the following blade, therefore decreasing the efficiency.
So when we're selecting components for a drive system, we first usually start with an initial guess for the propellers we want. So and we chose to use two-blade propellers for our drone this year because, as Madam mentioned, that two-blade propellers tend to be more efficient since they provide a cleaner airflow to each of the blades. So based off our design, based off our competition requirements and our design requirements, we were able to determine an average flight speed for that our drone needs to achieve to complete the mission, and we approximated mass for the drone, the final mass for the drone, and based on the approximation of weight and the flight speed we need, we could approximate lifting force that we need for the drone to fly. And using that lifting speed and the data available for various propellers, we determined that a 21-inch diameter and a 14-inch pitch propeller, the two-blade propeller, would be ideal to get the range that we need. Also, this number, the specifications for the propellers were partially determined through eCalc, where we chose a propeller size, chose certain battery, certain motors, and calculated the range that it could give us, and iterate through that to determine the ideal propeller size for a given drive power system. Yeah, so this turned out to be the ideal propeller for our range. So after a propeller has been chosen, we move on to choose motors. And since we have larger propellers for high efficiency and for the large lift force we need, we also need large motors with high torques to power these propellers. And with higher torque, apart from higher torque, we also need the propellers to rotate at a given RPM to provide the needed lifting force. So that means that we need the motors with high enough power rating to operate to get the range that we need. And so these were the three motors that were with our configuration. And we then, since total flight time is something that we have to consider, we chose the key motors M801S as the motor we be using on the drone, since it gave us the highest flying speed, cruise speed. After we have the motors, we have to spec out the batteries and the capacity of battery we need to operate the motors for the given time and achieve the given range, the range of 8 miles. So these are three considerations that we had, and so this is a 24 amp hour cell battery. So we chose LiPo battery. We chose LiPo batteries for their high energy mass to energy ratio and high energy density, and for LiPo batteries for their high energy. And since we didn't have batteries that were produce that are of the size we need. So we had batteries connected parallel and series. So here we have 4 12,000 milliamp hour batteries, which are 6 cells each, and you connect them in parallel to get 48,000 24,000 milliamp hour battery, which is 6 cell, and then we connect 2 of those in series to get a 12 cell 24 amp hour battery. And using this, we got a max range of 6.5 miles, and the total weight for these 4 batteries came out to be 6.5 kgs. Similarly, we had 16 amp hour batteries in parallel and series, and 22 amp hour batteries in parallel and series gave us these battery capacities. And something we noticed here that adding battery capacity certainly increased the range for us at this point. However, we noticed that as we move from 32 amp hours to 44 amp hours, the increase in range is just about a mile, but the increase in mass is about 2.5 kgs. So as we keep on increasing the battery capacity, we also keep on adding mass to the drone that needs to be lifted by the drone, which requires more battery, which requires more power up. So we chose to go with 32 amp hours as the battery because it gave us the range we needed, and also we had the costs in consideration when choosing.
All right, so next we'll look at the airframe and the overall structural system. So after matching the power system to the specifications from the motor and the propellers, that gives us enough speed to complete the mission in time. But at the same time, the overall size and compactness of the airframe will also affect the speed and range. Realize that in forward flight, the thrust is working against weight in vertical direction as well as drag in horizontal direction. So our main target here is really to achieve, to be able to carry all the payloads while reducing drag, so creating a very compact system. And the compactness is mostly dedicated by large batteries, as you can see on the contour. Electricals and various payloads. In particular, this year we're trying to integrate the rover or the UGV into the frame to eliminate drag. That's why the drone, the frame, the overall frame will also be increased in contrast to Condor last year. And in terms of the overall size, the spacing of the booms needs to be carefully considered because we don't want any tip-to-tip interaction when the propellers are spinning at very high speeds. And overall, the center of mass of the system and the center of lift need to be managed carefully to ensure that the flight is stable. And another goal that we want to achieve by the team is to keep on improving the overall structural soundness and material selection. Material selection is very critical in that process. So there is aluminum alloy and carbon fiber sheets. These two are very popular materials in creating airframe for aircraft applications. Both of them have very high respectable strength-to-weight ratio, but the team favors aluminum sheets primarily because it's cost-effective and it's very easy to manufacture for us in-house. And also realize that carbon fiber sheets are composite structures that are hard to predict the failures, and overall analysis is more complicated. That's why we're going with aluminum alloy 6061 this year, the same as the ones on Condor. So next we'll look at the frame design and what changes we made this year. As we've iterated before, we need to integrate the rover inside the airframe. So this year we're going with a rectangular envelope that is 300 by 200 millimeters. So the along the y-axis that has been elongated, creating rectangular shape. And we are continuing the success of using cutouts in all the plates, we removed up to 60% of excessive material while maximizing the strength to weight ratio. We also put our frame through simulations to test bending and torsion. And in summary, the worst case is bending the frame in the y-axis along its longest dimension. And we saw that maximum displacement at the tip of the booms or the tubes is 1 centimeter, and we think that is acceptable. And in all the plates, the highest volumes of stress we saw is 50% lower than the yield strength of the aluminum alloy. That gives us a safety factor of 1.5. And this just gives you a quick idea about how large we've allocated the space for payload on the airframe. It's 15 centimeters by 20 centimeters and just under 10 centimeters in height. And this here we have this large channel for the air drop during the mission, the third stage.
All right, so one extremely major departure from last year is the tube clamps. So as you can see on Condor, the tube clamps are clamped top and bottom. This time we're going with a side-to-side approach. And the reason for this is because we need to make them taller in order to accommodate payload. And of course, making them taller makes them more difficult to manufacture. This was proven to even be a challenge last year with Condor, with the smaller height. So we would have to drill farther, essentially, in order to just extend Condor's boom clamps. So it's kind of difficult to see, but there's a blind hole through the top and through holes through the sides here, as well as a blind hole down at the bottom. So the blind holes will be holding boom clamp to the frame, and the through holes will be clamping the boom itself. This design is also easier than Condor's because we can remove booms quickly and easily. While with Condor, we kind of have to disassemble the frame a little bit in order to get the booms out. This will let us quickly test and pull booms in and out of the sockets easily. And we also, through the test that Sean did, we found that it wasn't sacrificing the structural integrity of the frame by doing this easier to manufacture design.
So another component of the drone is the landing gear, as seen on Condor here. So the landing gear helps the drone stay stable when it's not flying, and it also helps the drone land after a flight. So we identified five major design considerations, which were stability. So it should be stable when it should be stable, and we wanted it to be stable on the fields, on grass, and on concrete, because we generally test our drone on the fields here at UBC, and we want it to be stable on concrete since we compete at on our competitions are on concrete, and we want the landing gear to be strong enough to handle reasonable drops by flying, or if something goes wrong and the drone drops from a reasonable height, the landing gear should be able to withstand that drop. Also, every time the drone lands, there is some stress that the landing gears have some internal stress that they undergo, and they should be able to withstand the fatigue cycles from these landings. And also, the landing gear contribute to the weight. So the weight, as in terms of mass and in terms of the drag, because these are landing gear tend to hang off the booms, and these create additional drag coefficients. So that's something that we accounted for as well. And lastly, since we have limited resources, cost and manufacturability of landing gears was something we have to consider. and this gave us the parameter weights for conducting our weighted decision ratios, where the weights were determined by how important we believe each of the components. So these are three design options that we had. So the first one was having the landing gear we have on Condor for a Newton as well. The second one was an embedded antenna. So on our drone, we have an antenna called the Bullet, and that antenna usually takes up quite a lot of volume. And so to optimize for the volume, we were considering an option where we could have the antenna go sit in the landing gear, and for that to work, for the antenna to be able to communicate, we would have to make the landing gear of composite materials such as fiberglass and carbon fiber. And lastly, we had an angle designed for the landing gear, as seen on the previous slide. And so these were three designs that we considered. And considering Condor as our base case, we scored each of the three designs qualitatively on the 5 criteria we had, and we determined that the angle landing gear as seen here would be the best design for this year's drone.
Okay, to summarize the presentation, you can see our CAD model here. So this year we're using a new landing gear compared to Condor. We're using a new frame compared to Condor with an embedded payload bay, and we're also using a new set of motors and propellers as well as batteries. Our main challenges this year are going to be minimizing our weight. So we need to create a light drone that's efficient and able to complete the mission. We want to be able to integrate our payload into frame to reduce drag, but this has problems with coordinating with the other teams and ensuring that everything works well within a deployment mechanism. Tying to that as well is we want to reduce drag with that aerodynamic frame, and that's going to be a challenge we're going to have to face down the line with how to integrate that into our existing design. We want to have a reliable airframe that's able to withstand the typical operating stresses. And as I touched on briefly, we need to integrate with the other teams. So that is not just payload, but that also includes software and the radio communications. And I think as Adam mentioned earlier, this is kind of the crucial part of the whole competition, is making sure that we can work well as a full integrated system. And then our final point is that we have to control our budget, as we do operate on a limited budget, and we want to be able to make sure that we can achieve all of our goals. So yeah, thank you. That's the end of our presentation. Again, I'll leave the link up here in case you guys didn't get it. But yeah, I'll open it up for questions.
So, can you talk a little bit more about the classification between going for a little bit more in depth about going for aluminum and carbon fiber, and maybe drawing on? I'm aiming this more at Oliver, so you can draw on like past experience maybe a little bit.
Yeah, so I think as Sean touched on the drone prior to Condor was Raven. It was a carbon fiber plate, and one of our biggest challenges with that drone was that it would A, have vibrations, and B, when it did sharp turns, it would wobble, and that made it hard for the flight controller to predict how it was going to react, and therefore there's a lot of troubles with flying it. So the aluminum frame provided us with the necessary rigidity last year, and in addition to that, as Sean touched on, it's a lot easier to manufacture and a lot easier to simulate and model, because carbon fiber is a composite material, and so it means that simulating it, you don't always, it's very complex, and it really only operates predictably when it's loaded in one direction. Yeah, anything else you want to
Yeah, and also compared to the Condor this year, the plate to plate distance is almost double to 10 centimeters. And that creates a lot of challenges. If we were to use carbon fiber plates, we need very large standoffs or multiple layers of plates, maybe 3 tiers. And we think overall that going with aluminum is the right design.
Any questions?
Yeah.
So are there any size restriction for the competition? Can you build this as big as you want, or was this your consideration of the size of the drone?
Yeah, I think the maximum size is 25.
That's
USC. Baby says 25 kilograms. 25 kilograms. So yeah, we're still coming in a bit underneath that, and that was just because we reached our range target and to keep our costs under control again.
Right. When you're going to be designing the shroud, are you going to be making it, let's say, asymmetrical so that the drone just flies? It always flies one direction, but I thought maybe you could generate some lift with the shroud as well. Say maybe on the batteries, are you going to be aiming for that?
Yeah, that's something we're looking at. We're looking at doing an airfoil design, but it's quite hard to pull off. And like I think that we are one of the few teams who's starting to look into this shroud design. And again, with the trying to make it into an airfoil to get the lift, it's quite it's even with the integration with payload, it's still pretty tall.
Mm-hmm.
So trying to avoid the flow separation is still it's hard to achieve. But we are trying to angle it, if that makes sense, because if you can imagine, like when the drone's flying, it's actually like flying at like a bit of an angle, right?
Yeah.
So it'll look kind of weird maybe, but it's not going to be pointing like this. It's going to be kind of pointing a little bit up, so that when it's flying, it's at that optimal shape.
Cool.
Yeah, I think our primary target of creating a shroud this year is to minimize drag, because as said in about eCalc, that it assumes a very exposed airframe. And I believe the algorithm is using a CD drag coefficient of roughly 1.3, and even if we do not use a highly optimized aeroshell, we can still bring that down by at least 50%. And that's assuming that the drag coming from the body is significant enough to outweigh the added weight, and we think it is.
Yeah, cool. I guess I'll just go through everything. Okay. What was that? Oh yeah, I was wondering, as it's probably it's just pennies, but maybe you could put the wires through the tubes and reduce some lift from that. I know it's just pennies, but I don't know. Would it be?
Yeah, no, we did think about that. There's some problems because, well, for one, it increases the length of the cable, which increases like electrical resistance. So that's one problem. And then you have to mount the ESCs in the frame and then have them run around. And so that's where we have a pretty tight space. So yeah, it's something we've considered, but and also serviceability is also a concern we have. In case anything breaks, like if an ESC breaks, we need to like rewire it through. It would be difficult, but yeah, no, this is a good point. Something we have considered in the past.
And last thing, this may be for another team. I was wondering if you could put the antenna maybe below, would it help a little bit? Because it's pointing out, it seems to me that maybe sometimes you cannot really have a direct visibility in through these bulky batteries. And I'm not an electrotechnician, but it seems that it could interfere with the signal a bit.
No, that's exactly what we're doing this year. We're going to do, the antennas are going to be mounted on the bottom edge of that frame, pointing downwards, or off to the side and up. And that's also just due to the spacing restrictions we have.
Yeah, I think the exact design is that we're going to mount it around here. Oh wow, I forgot to touch screen. It's too advanced. So we're going to mount it just roughly here, and we actually we're able to create angled antenna so that it can avoid just the edge of the frame here, sitting right behind the battery.
Awesome.
That's why I did that. Thank you. There's an aluminum cage right next to your antenna with it. I had some similar questions. I guess one of the things I can see from this kind of assuming they're using roughly the same size stocks and things. So I don't know how much help it would be, but did you ever consider using like an aluminum honeycomb instead of plate that you pull out of?
Yeah, that was
quite costly and using the stock.
Yeah, exactly. Yeah, it's like you're talking about like the honeycomb with carbon fiber, or like
Yeah,
something
there's a
like
few
that.
different versions.
Yeah, like that was something we looked at. And then yeah, like touched on, we're using quite thin plates, and they don't really make it that thin, or like they do. I don't know. It's harder to work with, and expensive, and manufacturing also kind of a concern. There we don't have super advanced equipment, but yeah, there was something we looked at, but I think due to like cost and just we've worked with aluminum before.
Yeah.
Yeah, it wouldn't. I mean, the weight saving is also not like gigantic, right? It's
You guys took away most of it, so it's not too
yeah.
I was curious with the battery calculations too, like you talked about a safety factor on the mechanical stress of the system, but do you have a safety factor on your battery range there? Because it sounded like everything calculated out to being able to perfectly just make it through the mission.
Yeah, so that is a thing. So for one, the calc range, the range it says there is conservative. Usually, like we found that on our previous drone, we were able to get more range out of it than what it said on there. So that gives us a bit of room. Additionally, I think we can, if necessary, we can do it. We can do the last part of the mission in less than 2 miles. And the shroud. We don't know exactly how much performance we're going to gain from that, but we think that it should at least give us slightly over what it says there. So, yeah, I mean, but yeah, it's not like we have a ton of room, but yeah.
Yeah, I guess my big concern there is that, like, aside from the drone not being able to make it through the whole course, but the communication systems, I imagine the quality of how all of that works is really dependent on having a good, clean electrical source.
Mm-hmm.
So I can imagine when those batteries start to run down, I can start to cause other problems there.
Yes,
maybe more related to other things.
Yeah, I think that the PDB ties into that. It tries to like regulate it a bit to make sure it stays clean. I don't know if you want to add anything.
Yeah, essentially as the batteries will deplete, there's still going to be because we're having a voltage of approximately like 50 volts, which is way higher than we need for any of our electronics. The PDB essentially has a bunch of voltage regulators on it for 12 volts, 5 volts, and 3.3 volts for all the smaller electronics. So that's not going to be much of an issue.
Yeah, the only other question I had was a little bit more about, I'm just not sure I have all the information, but for the clamp design that you were talking about, is there a particular reason that you were aiming to have it all like through hole nut and bolt, and you weren't just tapping the second half of the clamp to thread straight into? So it looked like it was the clamp with the bolt straight through it and then not on the far side. And then if you were to go one step further with that, you could potentially, since it looks like a water jet head profile, you could cut it as one piece with a flexure to it and just have a single fastening through it to clamp on. You could just simplify it that way.
We'll move it. You can just move it this way.
Yeah.
I wasn't sure if there was like another function of them that required it to be.
Yeah.
No, yeah, I mean that I like the idea of the flexure. That could actually that actually is not a bad idea. It's good. And then yeah, I think that we wanted to have the nut and bolt just because of like tightening. But I think that yeah, you do raise a point. We don't actually really need the nut.
I mean, it's nice to have symmetric pieces that, like, if one breaks or something, you can just use anything. So I can understand from that side. But yeah, I don't know if you simplify it a little bit more and saves you a little bit of weight as well.
Yeah, I mean, I think another thing is that another reason I went that was because aluminum, the threads can start to wear after a few screws and unscrews, and so we weren't sure like so having the through hole kind of solves that problem. We're also looking into anodizing where you can like do like a hard coat. on bottom ones?
No, you said you're anodizing the aluminum.
Yeah.
So you'll be able to anodize the outside.
Yeah.
You won't get any anodizing really down into the mold.
Okay.
Because it's an electrolytic process, you won't get any current density inside. So it's really hard to get any anodizing down inside the mold.
Yeah.
If you want to wear, then what you would do is put a helicoil in, stainless steel helicoil.
Yeah.
They're cheap and they're simple, and then you're wearing on the helicoil.
Yeah. Yeah.
That's good.
Thank you.
Yeah, the flex is.
Can I have some clarification on the flex drive? I'm sorry. It's just like the same thing, but like the bottom is still connected and it's just a slot on the top. Is that, yeah?
Yeah, so you could slot a little bit past the hole so that you have a little bit of touch flow range in the bottom as well. But yeah, the one piece is the two.
Sorry.
Yeah, I've got a few questions. So, sorry, back to the first presentation, you talked about the telemetry, you had like dual systems.
Mm-hmm.
So how do you tend to implement that redundancy? So are you polling both systems and comparing like a certain error to say that, okay, one of them's failed, or
Yeah.
how do you know?
Yeah, I mean, I think Eric can probably explain it better than I can, but I think it's basically like some kind of system that compares the two and.
We do essentially just we pull both, and we take the latest one. So because they're timestamped at like the Skylink application will timestamp when it grabbed the telemetry, and we pull, and whichever one just happens to have the newest telemetry, because we pull it once a second. We just use that one instead. So then if one's not there, it obviously can't be newer.
So you're just saying, so it's redundancy only in a complete failure, not in inaccurate. So
yeah.
Okay. So you're not doing a tiebreaker to say, okay, we now have two that aren't the same. Which one do I believe? You need to go in with some other data to figure out which one's right.
We don't do that yet.
Okay.
That is a good idea.
That's the whole idea of a redundant system.
Yeah, exactly.
Is because they don't always fail completely.
Yeah.
Right.
So maybe some sort of checksum as well.
Yeah.
Yeah.
I think our focus on redundancy here is in like the wireless network loss, because of a ton of time to fail on our part just because they're kind of a delicate part of the aircraft, or just different frequencies behave slightly different with obstacles in between them. And it's generally always a network failure that we have, or like a wireless failure, not necessarily a hardware failure.
So the landing gear, I mean, the landing gear is a necessary evil, but is there, like when I look at the structure, I want to take that landing gear and make it the structure. Like right now, it's just parasitic. So is there a way of incorporating the structure of the landing gear to stiffen the entire structure? So you imagine if this was a complete truss structure, so you have that depth to give you reinforcement, and it's landing gear and structure. Since you've got the drag of it, you have the weight of it, then you could make the structure incredibly flat. Right? Because these are completely bending, which is like the worst, most inefficient structure. So the more you can put things in tension and compression, you can have flat structures. So, it's kind of late in the game to entertain a wild idea like that, but it would be neat if you could do that. Do they have to be this? What's the purpose of them being this high?
So for on Condor, the plate isn't here, but there was a plate here that would do the how all the electronics,
right.
And then another one below that had the rover was hanging off of that. So you needed basically all this height. But again on Kestrel, we're going to be doing a integrated bay, so we're bringing that height down a bit. I think it's
So yeah, you make that higher base so you could get the electronics in that box, or is that for the winch, or what goes in that core there?
Yeah, so the box has the winch and the rover or UGV. But yeah, so we could actually even reduce the size more.
So could you expand that center structure and bury the batteries in there. Like the more things you can get in that center structure, reduce the height of it, then you put your shroud on, you're gonna have much better aerodynamics, right?
Yeah, so that was something that would be nice if we could do. We're already kind of pushing it with the height as it is right there, just due to the spacing between the plates. Yeah, that was something we looked at, but I think just because of the pure amount of battery we had, it wasn't going to be feasible this year. But I mean, I think that is something that we would want to be looking at in the future for sure. Yeah.
And the batteries, these come in a box, or you assemble like C cells together to build a battery? Or?
They come as a you can
As 6 cells.
Yeah.
6 cells.
Yeah, 6 cells.
Because what I want to do is I want to put batteries in all your booms.
Yeah.
Because like putting fuel in the wing, right? You reduce the bending moment. Might as well put the weight out there where you got the lift, not here where you've got thrust to lift it.
Yeah.
So in an ideal world, you put the batteries in there.
Yeah, we've talked about that, and I think that's definitely where we want to be very soon. There's a lot of benefit to building our own battery packs, both in just like availability of cells and customizing the shape so we can kind of pack it in all the corners, like you said. That's definitely something we're thinking about. I don't think we quite have the resources or time or like confidence in successful completion. But I think we definitely as a team want to get there very soon.
Yeah, I know that some companies have started looking into that, doing like structural batteries basically, where it's a very light frame and the batteries provide like most of the support, and they can get really long ranges with that. But,
Yeah, that's a little scary. The first step is just get the mass where you want the mass, right? And I guess I would challenge you on the carbon fiber, but I know if you don't have the resources or the experience, it's kind of a new area, but you can. Modern aircraft have a lot more carbon fiber for the reason you can't beat the stiffness to weight ratio, you can't beat the strength to weight ratio. So, but it's a different technology. So you're gonna go with aluminum. Why did you choose 6061?
Versus like say 7075.
775, 2024.
Yeah, so yeah, we looked into that. That may be something we consider down the line. It's a little bit harder to work with, more expensive. To be honest, we have a lot of aluminum 61 already. So, and then I think we just did the gains were kind of marginal. Not marginal, but they weren't like that significant. But I think we might look into doing it, like rebuilding the frame later in the year if we have money left over.
Well, I mean, yield on 775 is what? It's got to be 50% higher?
So I looked into that last year on Condor, and 775 obviously has a much higher yield, but I found that we're mostly interested in like stiffness, and the 775 doesn't have a better stiffness for sand construction.
No, absolutely. So
like we're worried about the deflection of the frame far before we're worried about the actual yield.
Right. But if you could optimize it more, so you're actually using the material in tension and really pushing it, then I think you could exploit it. I mean, it could. You're right. I mean, most of the time, I mean, that's the trouble. In bending, it's deflection limited, and so it doesn't matter what you use. It's just that you'll find those areas when you do a stress analysis, you find high stresses that the 775 just gives you so much more margin. It's harder, but it machines beautifully. It cuts fills nicely. It's got a water jet just as well as 661.
Yeah.
And for the little map you're using, I would think it would be much better.
Yeah, it's not. I mean, it's written in Canada for some reason. It's our usual supplier is a lot more expensive, but we can find it elsewhere. Yeah, it definitely we'll look into it once we later in the year. Yeah, for sure.
And the landing gear, it doesn't look like you need any flex in it, so you you land soft enough that flex isn't an issue?
In an ideal case, yeah. Sorry?
Under normal conditions.
Yeah, under normal conditions it wouldn't matter. But yeah, we need to have, because we have lost. It's sometimes you'll lose connection like right above the ground, and so it'll drop like 10 feet or something. Or in initial flight tests, it's a little bit more shaky, so we need that redundancy, and sometimes you accidentally just let it drop too far, and so it needs a little bit of.
So when these have crashed, what fails typically? Like the booms or the attachments?
Well, actually, this one hasn't. Well, no.
Tubes always break.
The booms. Yeah, the booms crack. These motor mounts were replaced after a crash because they warped a bit. And then our previous drone, there was a couple hard landings and the landing gear deformed.
I'm just wondering, I guess you have some reason for it, but putting the gears so close and the propellers to further from from all of, is it not gonna put a lot of stress on the body, especially in these hard landings? I was wondering, you could put them a little closer, put it down. I don't know.
So there's two things to balance there. Yeah, they definitely can be a little bit closer to the body, and they probably should be. But the other thing to consider is often, mostly in our Canadian competition, it's quite windy on the flight line, and having a wider base gives you a lot of stability in preventing the aircraft from rolling right on takeoff. Like that's kind of the most likely point that you roll, and I think 2 years ago, like half of the team slipped over right as they were taking off. And we learned quite quickly that a really wide base in your landing gear is kind of the easiest way to prevent that.
That actually might be one of my questions from before, and I think this might have just been being 100% on when we were talking about it. We were talking about your 1.5 times safety factor on the stress of the body. I'm sorry, I didn't catch what the load was that you were basing that around. Was it your cargo payload or some sort of like shock load crash landing?
Yeah, so we did some preliminary FEA analysis. Basically, we consider the worst kind of bending case, which is fixing these two booms and then really bending this upward really hard, putting a lot of stresses on the frame here. And so the load we used is actually the maximum theoretical thrust provided by the manufacturer, and those actually use even bigger props, so much larger thrusts are generated. And we use those forces, while in reality our forces will probably be far less. Yeah.
How would that first compare to the shock of it dropping, say, from the height of the table onto the ground horizontally?
I think we did some dynamic tests on the landing gear.
On the landing gear, where we did dynamic tests to see where the stresses would be divided if we fall and we drop from 10 feet. So consider the velocity that we have just before drop and conducted a dynamic test for that. And it's usually the sides of the landing gear that have the stress, that carry the stress, and the booms that have where the stresses are transferred.
So you're saying the body isn't the weak point of that?
Yeah, the body, the clamps have some stress as well, but the body, the frame internal doesn't.
I think in the worst case scenario, it's gonna experience the most amount of stress. Oh, sorry, the most amount of stress just here.
Yeah.
So then this is gonna just bend and deform a little bit, and then that still gives us usability.
Yeah, I mean, again, just on that maximum thrust, that's basically considering the scenario where we're going at max speed and then you want to stop or make a hard turn, because that was where we had the problem with our drone before this one with the deflection and the.
Right. So what does that work out to how many G's? What's the maximum volt? Have you worked out a flight envelope?
I don't think we did the G's yet because that wouldn't we have to do a more full simulation, I guess, like a full to get that value. But like you said, he just considered like basically if it's delivering the maximum amount of thrust that it possibly can.
I'm trying to remember. I think we have our flight controller basically maxed out in its acceleration, and I think we get about like 0.2 G. Not a lot.
Yeah, it's just that you're going to have maneuvering loads from the flare. And you're going to have lift from these, and you're going to have the inertia of that. Like typically with an helicopter, you're around 3 Gs is kind of the maximum you need to be able to withstand in maneuvering.
Mm-hmm.
So, you'd want to make sure that, okay, if I had 3 Gs in the center there, is that going to withstand that? The landing loads is a separate case altogether.
Yeah.
Is that, do your drop test and figure out. But again, the loads are going to be different on the, because the G force is different when you're maneuvering versus when you've got plane loads. Those are 2 cases.
Yeah, we definitely should do more dynamic tests. But so far in our bending test, we sort of just put all the weight on the center plates and then the thrust on the booms for now. But yeah, we should. I think we did calculate some impulse when we're like coming to a sudden stop, considering the forces that's needed, including the weight of the overall structure and the speed. I think we did like 0.2 seconds stop.
So have you got accelerometer around this?
Yeah.
For your stability. So have you, when you've done the most crazy maneuvers, you looked at it, did you get readout from that? Can you see how many Gs you go?
Yeah, I think like you said,
That's what you're saying?
I'm realizing what I said, I think is what we basically set our flight controller to, but I'm sure we can get it much higher than that. I don't remember. I mean, we have access to that data. I don't remember what the numbers are.
Because that would be interesting to just go out and do the most crazy maneuver and see what it is, and then feed that back into instruction and say, okay, what margins do I need to have?
Yeah.
All right, I think I'll probably give it like a 5-minute break. Thank you guys for all those comments. That's
great.
Yeah, absolutely fantastic. I think we're really grateful for all the feedback. I will, just because I know that everyone's gonna have to go home eventually, unfortunately. I know. So I guess we'll do like a 5-minute break. If you guys want to grab this Steakers pizza, there's also some more water and some more food, and then also just take 5 minutes if people need to run the washroom or anything. And then if Emily wants to go ahead and give payload a go. Yeah? All right.
You guys want to stick around?
Oh, yeah.
If you guys need to be places.
We have no
We have to deliver a UGV to a predetermined location. Here, yeah. So there's a stranded hiker. We have to deliver a UGV, which is an unmanned ground vehicle or a rover, from 100 feet above the ground, which is the minimum altitude that we're allowed to fly, and it has to be within 40-foot radius of the GPS location that's given to us. Once the UGV has landed, it must autonomously go to a second location, delivering a 250 milliliter or 8 fluid ounce water bottle to a stranded hiker. So you see a lot of Imperial units because this competition takes part in the US. So I do my best to kind of convey to you metrics that are applicable. Yeah, so going into this challenge, we had a few priorities that would affect our strategy. So each year at competition, there's in the past been 75 teams, this year there's 150, and we actually see a very low completion rate of the missions. Just just getting the mission completed will get you points and get you high up in the scoreboard. We'll easily land in the top 50% of teams, just getting 1 point for the mission part. So we are limited to about we have 8 months total to design and build the system. We are trying to condense that to 4 months so that we can focus on testing in the second semester, the second 4 months. And so heavily time limited. So we wanted to focus on having something that works first before we have something that works perfectly. I think a lot of students go into that pitfall of making the perfect design on their CAD system before trying to implement it. So that was what led us to being prototype focused. We wanted to make sure that the system was working, that we could iron out any kinks, so that we weren't making any invalid assumptions, and just kind of fail early so that we could be successful later on. And then the final priority that we have is to add some UBC UAS flair. We're lucky to be a student team where we can take high risk choices and decisions in a low stakes environment. And so, yeah, we really wanted to use an excuse to exert some creativity. And as well, we can't expect to win and to beat every team if we're doing the same thing as them. So we definitely wanted to bring a novel aspect to the design for our own enjoyment and learning experience. So, yeah, so the system, we broke it down into 2 parts, just to focus on the problems in isolation, and that way we could get it working so that later on we can integrate them and focus on getting that to work. So we broke it down into an airdrop, so we focus on lowering we're assuming to be a 1 kilogram object from 100 feet to a precise location. And then the second one would be having a rover that once it's on the ground, it can travel to a second location within about 10 minutes, and it autonomously, yeah. So going into this presentation, I'm going to break it up into the design process for the airdrop and the design process for the rover separately, because they're quite separate. Yeah. So we broke down the airdrop requirements based on the rules and based on some of the restrictions that we had as a team. So we wanted it to drop at no more than 1 meters per second. We estimated that the capacity for the rover before it broke would be 2 newtons, so the impact force at 1 meter per second would be 1 newton. So we added a bit of a safety factor there because it was quite a crude assumption. And so the rules state that the UGV must be functional when it hits the ground in order to get the points. And the competition defines functional as it is able to move, as it was intended to. And the water bottom must remain intact, as that's the most essential part of the scenario is the delivery part. So it needs to be working for us to get any points despite the accuracy of the drop. The other thing is we wanted to reduce the drop time. So we have had similar airdrop projects in the past, and we're kind of using that as a benchmark to improve upon. So our drop time at that point was 30 seconds, and so anything better we are happy with, it's worth pursuing. And so there's no actual restriction in the competition rules for how fast or for how long we need to drop it. But if we are taking too much time, we're taking away valuable flight time. We have about 30 minutes total. So those few seconds could be used to identify another object and get us even more points and higher up the scoreboard. Because as you get to the top, the few points really makes a huge difference. And the 30 seconds, that extension. And the other thing, we wanted it to weigh less than 200 grams. Again, a similar concept that we've done in the past was 200 grams. That was, I'll touch on it a little bit later, but it was a motorized spool. And so we wanted anything that's better. But as well, we've been allotted 2 kilograms total for the payload. And so this, we assume that 200 would be enough to allow for a camera, a rover, and some of our other telemetry components. And the other thing is it needs to land within 40 feet. That's the 0 point mark if we're beyond 40 feet. To get 100 points, 100% of the points, we have to be within 5 feet. So obviously that's the goal. But to get some points is better than nothing. So here are some of the most competitive concepts that we took going into it. So the motorized spool, which was a concept from previous years, where the motor creates resistance in unwinding the spool, so it will run in reverse to the way that it naturally wants to unwind. And then once the payload is released, we want to reel it back in, because as we get to the last few rolls around the spool, it actually loses its grip on the spool, so it has to be fixed. The rope has to be fixed to the spool, so we have to reel it back in. The friction braking idea is a novel idea this year, where we place a rope between two braking pads, and we have exactly 100 feet of rope stored, and once it falls through, the 100 feet falls through the pads, and the drone is able to fly away without having to bring the rope back in. We would control the normal force on the rope by using a linear actuator, and that would control the friction and slow it down. So then the other concept that was competitive was a parachute. This is something that we actually did in testing last year, where it's pretty self-explanatory. You release the rover and hope for the best. So here's a brief summary of our evaluation process. This is more of a compilation of some of the WDMs and other evaluation tools we use. So this doesn't account for the weights of all of our criteria here, but we can see that some ideas are a lot more consistent than others. We set the motorized spool to be our datum, as it's something that we've actually manufactured in the past. So the friction braking is stronger in a lot of aspects, mostly the weight. A linear servo that we had spec'd out was 15 grams versus the 50-gram motor that the motorized spool used, so there's a considerable weight savings there. And as well, the execution time is essentially halved, because once it falls through, the drone can fly away, you don't need to do it back in. And the space as well, you do get a lot more compact, because there's no rotating parts. You actually don't need to shield it, you don't need to worry about rope getting caught, or things, or dust getting in there, and ruining the efficiency of, I don't think the efficiency of it, but, and also, when we use the motorized spool, we have to get a rather large torque, so we had to use quite a big gear, which was bulky. Yeah, and in comparison to the parachute, it's very strong, but it's also very weak in other aspects. So the parachute is obviously one of the lightest ones. You would only need a release servo, which is 9 grams compared to the other ideas, and you would use less rope and material to hold it into the drone. And the drone can take off as soon as the rope is released, the parachute is released, so you don't have to wait for it to fall to the bottom. It's a matter of seconds before it's gone. But where it's the weakest is that it's completely pure luck as to whether it gets to where you want it to go. It depends on the initial trajectory and the weather that day. It might hit a gust of wind. But I think where it fails the most, where it matters the most to us, we've got 3 minuses here, is that in testing last year, the parachute actually deployed early. And we got very lucky that it broke off and fell straight to the ground. I think Adam can attest to it a little bit better than I can. But it actually got sucked out of the compartment or something, right?
Yeah, so it was that what the container that was holding the parachute, like a little bit of the parachute actually kind of slipped out of the container, and then basically one caught it and it came out. And lucky for us, yeah, it was kind of attached to the aircraft through a key ring, and then there was an actuator that sort of let that key ring go, so the key ring just snapped, like similar to just like the standard key rings. But yeah, that sort of gives you an idea of like the amount of force that literally snapped that key ring. So if it hadn't been for that, it could have pulled down the whole drone. So that was lucky for us. But
yeah, a big concern would be getting the cord stuck in the propellers and bringing the whole drone to the ground, and that's the absolute worst failure mode that we can get out of this. So even in testing, it was not worth pursuing a risk like that. And so yeah, the difference between the parachute is that the risk or the downsides to it are inherent to the design. That there's a lot of drag, so there's a lot of force on it that it can do all sorts of crazy things. Versus the weakness in the novel friction braking design is that it's not tried and true, and so it takes a lot more effort to get it to a working stage. But that was a risk that we can avert by putting in more effort. And quite frankly, we were more excited too because of the novel idea. Yeah, so sticking to our prototyping philosophy, here's the sort of prototyping evolution that we've done over the past few months. So this was our very first iteration. You can see a couple of rubber pads. I think this is EPDM. And we put it together using a rubber band, which would be our normal force that we were controlling with the servo. But through this, well, we found out that it's possible to create enough friction by using the pads and using rubber bands to hold the 1 kilogram mass. But we actually realized that having the spring force and tension, it actually wasn't accomplishing what we were trying to do in increasing the normal force, because this setup relies on contact between the rope that would go between this, that once you pull it apart and release the tension, you're just going to lose the contact and lose friction altogether. So we realized quickly that it's possible, but we need to do compression. So that's what spanned this preliminary design. We actually did it laser cutting, thanks to Xavier's laser cutter, and Luke's time. So we actually laser cut some panels and put it together. We used a lot of epoxy here. So we actually found out that tolerancing was a huge issue, that we were constantly having to re-drill holes because we couldn't really account for tolerancing when we were designing it, just because we were remote, we don't have the time. But we ended up having to use a lot of epoxy in like filling gaps and stuff because we didn't quite have the contact we needed. Yeah, re-drilling holes, things were stiff, these plates were a little bit too stiff on the inside walls, and just epoxy was getting everywhere, and wood and epoxy is a very difficult combo to work with. So moving on from there, we are continuing with 3D printing and plastic, just because it's a little bit easier and it's quick and it's cheap. And so here was us getting the mechanism to work. It worked like we wanted it to. You can see it's quite heavily strapped down, and that's because it was a little bit weaker than we expected it to be. So that was these are some of the things that our final design addresses, but it works. We actually did hold up a 1 kilogram mass with the linear servo at full extension. So at this point, it would just be a case of tuning it and getting the normal forces that we want. Okay, so here is our design going forward into the final manufacturing phase. So here's the inner mechanism that you've seen working. So we've got the compression spring, we've got 2 pads, and we've got stainless steel rods here just to act as a bushing, or to reduce the friction between the sliding plates. And then we've just got bottom and top plates to hold everything together and stable. And in this final design, we've also got some, you can see it at the back, this is a section view, but we've got some walls to kind of shield the sliding plates just a little bit. But yeah, so that's in terms of the structure. So the control sequence of this winch is what we're calling it because we can't think of a more suitable name. So the control sequence of this winch would be the rope will feed between these 2 rubber plates, and as it comes out, it will skim past a pulley. So the pulley will be lined with, at the moment, it's a rubber band just to make sure that the rope isn't sliding past it. And so it will spin the pulley, which is attached to an encoder. The encoder will give us rotational velocity and position that we can turn into the downward velocity of our rover or payload, and we can use that information to alter the normal force on the linear actuator. So one thing that we made sure to do was make sure there was complements, that the spring and the linear actuator complemented each other. So the linear actuator actually has a maximum force of 50 newtons, but it's most efficient at 40 newtons, and we kind of used that to keep it. We wanted to go 10 newtons under the max just to make sure that we had some room for error. And it has a 20 millimeter stroke. So we used that to calculate our spring, which would be more than we wanted it to be not too much more than 20 millimeters for space savings, but it had to be long enough. And the spring constant here does match the 40 newtons over 20 millimeters. And yeah, we wanted to make sure that the outer diameter was significant so that we had some sort of a minimum constraint in that it wasn't going to rotate and bind on the rods here. Yeah, so this is our design moving forward. We are still, in terms of materials, we're still looking at what friction pads to use. So in our testing, we've used, oh, wrong way. So we've used EDPM, and here, I can't really see it, but there's acrylic. So we've tested a little bit of both, and basically with the, EPDM, it's actually the coefficient of friction, the static coefficient of friction is a little bit too high. That getting the point between it holding it and releasing it, we have to have the linear actuator almost fully released. So we have very little resolution. The spring's almost at the top before we have some sort of speed control. And then with the acrylic, it's the exact opposite, where our coefficient of static friction was way too low, and that we were getting it to release fully at about the 25% release mark. So we're struggling to find a material that's somewhere in the middle, but that's just going to be through testing out different materials. It's small enough that that's cheap enough to do through trial and error. Coefficient of friction is really difficult to determine, especially when we're constantly running ropes through it, because the abrasion is constantly changing the shape of it. Yeah, and a note on abrasion, the rope we plan on using. So we've tested out lots of different types of ropes of different thicknesses, different materials, and our biggest concern is space and weight savings. So bigger, thicker ropes obviously have a lot more friction, but they're a lot bulkier and heavier. And actually we found that ropes and strings with circular cross-section were cutting into our pads and creating a groove for it to sit on, and there'd be no friction. So when we switched to ribbon. The two types of ribbon that we've used are like regular silk ribbon and actually gift ribbon, like the shiny stuff they put on presents. And although it gets a lot of weird looks, the gift ribbon is actually one of our most successful ones so far, just because the friction seems to complement a lot of things. It's a little bit higher than the silk. But in terms of we're sacrificing maybe, perhaps, arguably a little bit of professionalism by using but it's certainly a talking point for dinner parties. Yeah, so that's another thing, is that the ribbon will also depend on what material we're using for the pads. So that's kind of where we're going next, is the refining the materials, and lots of trial and error testing there. Okay. So moving on to the rover, it's a lot, so the requirements here is a lot more restricted, and so it's a lot less creativity and concept here. But so basically it needs to hold the 250 milliliter water bottle, and that's because it's the core part of the mission. As well, it must have an average velocity of 8.3 centimeters. We assumed we'd have 10 minutes to complete the go-to goal. So once the rover is dropped, there's no restriction on it getting to its second location, apart from that it must be within the flight window, and it actually cannot travel more than 20 centimeters per second. So 8.3 centimeters would be the minimum that we would need to get if we're assuming the maximum distance that we have to travel in 10 minutes. But we would expect to be less distance and probably a bit faster. And then the rover as a whole must weigh less than 1.3 kilograms. Again, this is an improvement from last year's benchmark, that we had a very similar rover drop situation. And as well, it fits within our 2 kilogram allocation from the aircraft. And the rover needs to fit within 10 by 14 by 20 centimeters. And so this is to do with the payload compartment that you guys saw in the other presentation. So it's quite a tight requirement, and it definitely ruled out most of our concepts. So these are sort of the concepts going in. So here, it might not be obvious, but this is actually a 3-wheel rover. We've got a little caster wheel at the back. And the biggest difference between these is that, so they both have direct drive wheels, differential turning, but the biggest difference is that this one is balanced by the third wheel, which is free spinning. And this one is balanced by aligning the center of gravity with the center, which is quite a challenge. Okay, so similar sort of idea where we are comparing the concepts relatively. So the three-wheeled rover, the two-wheeled rover is obviously a lot less weight and a lot less space, just because you're cutting out an extra wheel. You don't need the chassis and the support material to attach that wheel, and the weight savings is quite significant, especially on that scale. In our prototypes, our very, very early prototypes, we're seeing maybe like 50%, a 50% difference, or it would at least, yeah. And but where it's weakest is that the stability is quite a problem, because you have to make sure that your alignment of the center of gravity is really robust. But we decided that it's not actually a huge issue of drag. I mean, yes, we're getting less speed. Yes, it's quite a resistance. We might need even more power to account for that. But at the end of the day, if we can get to that second location, it doesn't matter if it dragged all the way to get there. So, and the other thing is that the biggest factor of the two-wheel design that made it the winning concept for us was that it can land in any orientation, so there's no backward and forwards. And if you're cutting out all the turning that you need to do with the differential turning, you're giving the compass less data to be confused by. So that's the reasoning there that we went to pursue the two-wheeled rover. But the beauty of this project is that if the two-wheeled rover doesn't quite work out, that the stability is a huge issue, we can just slap the caster wheel on the bottom, and that's getting the best of both worlds. So here is our most recent functional rover prototype. We wanted to do big wheels to have all the weight below it to maintain the stability. It's very crudely balanced here. We've got the water bottle is manually adjusted, and we have the electronics also manually adjusted, done by eye. But it makes it over big obstacles, and that's because the big wheels offer a lot more torque. But there are a lot more improvements coming from here that we want it to be a lot more robust alignment of the center of gravity. So the way we intend to do this is by having more rigid mountings. We also did some mass property analysis. We drew up the water bottle, gave it a density of water, and found the center of gravity of that. So that will help to align the center of gravity a little bit more exactly. And this model here, the wheels are actually 130 millimeters in diameter, which is too big for the payload compartment. So that was definitely something we need to do, is work on condensing the design even more. And weight reduction, so we're underneath the requirement at this point. This point was 850 grams, but the more the better. So that's the idea there. Yeah, so we still have yet to make a prototype of focusing on these improvements, so more validation will be needed from this final design. But basically you can see here that, so we reduced the size of the wheels, or reduced the thickness to reduce the size. We also made, so in the previous one we had a plank of wood that the water bottle was zip tied to underneath. So this one, we wanted to move the water bottle up into the chassis a bit more for height savings. As well, we wanted to have the water bottle held in a more exact way. We chose to do it these little arcs so that we could actually cut it out of wood as well. And we have a lot of surface flat area to glue things together. And yeah, so we have our motors at the bottom here. Our motors are 6-volt, 313 to 1 gear ratio. So this was, we traced back our required speed, which was 8.3 centimeters per second, and we took the diameter of the wheels and used that, traced that back to the RPM and the gear ratio that we need. So that's how we spec them. That's how we spec the motors. We also wanted more rigid mounts. So similar to the water bottle just being zip tied on, in the last one, the motors were just glued on, also done by eye. So we wanted more rigid mounts that were actually with locating features. So it's not very obvious here, but we've got some holes here to locate where the motor should go. So it's a lot so it's a lot more aligned, and there's no room for human error. And just making mounts for electronics to be a lot more stable, as low down as we can, and as many ways we can make it rigid. The reason why we wanted to 3D print the wheels is because the wheels are super hard to find the wheels and specifications that we need. So in the previous prototype, you saw that we used rubber bands to create the tires. That's something we'll probably continue to test with, but another option would be we have a TPU printer, or a printer capable of printing with TPU, which is softer plastic, which it adds a little bit of friction, but it's not comparable to rubber bands. So there's a bit of a trade-off between the preciseness of TPU and the grip that we have with rubber bands. Yeah, I think I covered everything with this design. We can come back to it if I haven't. But so to summarize the system overview and the sort of the flow of events will be, so the drone will fly over to our location and the rover will be lowered to our drop location within 40 feet, of course, or 5 if we can help it. And once the rover has hit the ground, the rope will fold through the pads and will fold through onto the ground and spiral up nicely. And the drone will fly away, and the rover, we intend to release it from the rope, and the rover can drive to its goal. So that's the sequence of events. So moving forward, the next thing what we will do will be integrating our airdrop and our rover. So we want to make sure that we can release the rope when it hits the bottom, that we have communication between the two so that the rover knows when it's on the ground. I think those are the biggest points. The other thing is we want to do a lot more failure analysis. So we want to look at the biggest ways that it can fail. One thing that a lot of teams struggle with in previous competitions and ourselves in testing previously was that early deployment was a huge issue, and you do get dock points for things falling off the aircraft, which is anything being lowered when it's not supposed to. So we want to create a binary clamp onto the drone to, it will only release once the rover needs to be released, once it receives the signal that it's in the right location. And so therefore, we don't require the winch to be closed at all times, only when it's in action. And as well, the binary clamp can close it if anything is wrong. Yeah, and I think there are more failure analysis that will come with the integration testing, but that's the big one we'll probably focus on next. And the final thing is optimization. I think anyone who has experience either working as a co-op or working in the aircraft industry is that weight reduction is everything. And so although we're under a requirement and we're on track to meet 1 kilograms, we actually want to reduce that even more because I believe it's a linear relation between the weight savings and the efficiency of our aircraft. And so another thing would be space allocation efficiency. Right now we're pushing the borders of the aircraft compartment, and so we really want to have some contingency where we can so that we don't have to worry about things getting caught as they fall. Yeah. So, questions?
Your pink ribbon.
So the first one was red and shiny, and then they convinced me to go for black, but I still went for shiny, so it's a bit of a compromise.
So how is it stored in this?
Yeah, so that's the one thing I didn't touch on was the next thing, part of system integration will be how everything fits into the compartment, because that's one of the things. These wheels are already the maximum height, and so our winch will be located, it will hopefully sit within the wheels. And yeah, and so basically the spool, we've got some space to store electronics. Electronics are not finalized yet, but we've got some space to store electronics at the bottom as well as the splat area on top, but we're hoping to keep some real estate on the top somewhere that we can have like a free spinning spool where the ribbon will be wrapped around the spool just to keep it untangled and out of the way. But as it pulls through, it will just unravel. There's no sort of motorization in the spool at all. Another thing we considered was the way that parachutes store their cord. So they fold it into the bag so that, it's not curling. I'm not quite sure the reason behind it, but that was some other thing we considered, but it seemed a little bit more bulky, that it wasn't as efficient space allocation.
I was just wondering, you guys are trying to break the road. I was wondering, could you maybe just do like a classical car brakes where you would just actually break the spool instead of the rope? Maybe you could apply the force like more gradually and nicely and control the speed better than just breaking the rope itself.
Right. So that was something we did consider, but we had a lot of trouble with rotating spools in the sense that, if we did something like that, we would have to rigidly attach the rope to the spool, because as it unravels the last few rotations, it loses grip and it just falls off completely. So you might have an excess of 1 or 2 meters that just fall off the spool. And so that would entail rolling back in, which is it costs a lot of time. And so we decided to steer away from the spools, mostly for that reason.
Go ahead, Jim. I was just thinking about your brake system there.
Sure.
And I realized that in reality it might not be exactly as normal, but often one of the issues with like a clamping brake like that is kind of the edge effect, like around the edges of your clamps. So if you have a sharp corner like that, maybe there's a burr to it, maybe not. As the cord goes through it, wears and it really adjusts how it clamps.
Right.
I'm gonna go back to my suggestions of lectures from earlier and say one way that you could maybe adjust this design that might also help your friction is to play more with surface area contact instead of necessarily the material. And if you could imagine making using a shim of metal to make kind of a arc shape for one side of it, as you push it forward. Sorry, I'm still trying to clean it through as I'm saying it. As you push it forward, the flexure or the shim would kind of deflect to flatten out and give you more and more surface contact.
Right.
And it also gives you then a smooth lead-in on the contact.
Okay.
Yeah, I would go towards this one. Maybe we're taking a look at climbing. In climbing, we have lots of different belaying devices, which just works on some sort of friction. I can also imagine that changing the surface, the friction would allow you better control with less of the movement of the actuator.
Right.
Maybe you can take some inspiration of these. There's at least 5 different kinds, which all operate on this principle.
Yeah, our linear servo has a resolution of 5 microns. So with this design, it's kind of banking on the fact that that would be enough to see significant changes in speed. But that's interesting. I'm personally not familiar with climbing, so I'll look into it.
Well, one thing I was wondering, are you concerned about the rope getting in the way of the rover and entangling it?
Yeah.
Maybe would you just fly the rope a little bit away?
Yeah, that's something. So one thing we're considering is dropping it, and as it's about to hit the ground, it will start moving, so that just straight off the bat, it moves away from where the rope is going to drop. We've done some drop testing with the rope, and it actually does coil into a nice, especially the gift ribbon, which already naturally wants to curl. It does coil into a nice thing, nice little circle at the bottom. And so we're hoping with the big tires, we're kind of keeping the rotating axles away from the rope enough, and that it can be enough to just climb over it. But that's something as well. Even if it does get caught, as long as it can move somewhat to the goal, it's not necessarily catastrophic failure.
You could, I don't know if this is what you were getting to, but once the rover's on the ground, then with some slack, you can lay lay the rope out a better way before the drop. That's what you were talking about?
Yeah, I was wondering whether the drone could kind of like remove the layer a little bit.
It could be. We could add so this relies on having exactly 100 feet of rope. I think so. Our drone contour has an uncertainty of what's the number? Do you know off the top of your head?
For altitude?
Yeah. it's super. It's
4 feet.
Yeah, it's super accurate. So as long as we can, yeah. okay, I don't know where how to get involved, but yeah, including more rope, and then being able to fly away, because it will passively release if you fly away and have extra rope. It should hopefully pull it away, so it could be something that we can add into our.
How do you detach it from the rover?
So we're thinking. So that's something we're still designing because it needs to be able to hold on to the full weight of the rover. So we're thinking of using having two loops here and a pin that will go through it that we can release. But yeah, in previous testing of the parachute, we saw that failed, but the parachute would have a lot more stress than this situation. So that's our initial idea for that. Another option might be rack and pinion. But yeah, that's something as well we have to still fine tune.
You talked about a motor design, so that was just you're just adding torque to the motor to limit how it came down? Is that your idea of the motor design?
Actually I personally wasn't involved with the design, so I'm not entirely familiar with all of the mechanics of it. I don't know if
that's kind of what was attempted last year is basically a drum and a motor with a gear system between them. That design also had a separate sort of crude friction brake on the side of the drum. We found a lot of problems with the braking mechanism just in rotation, and the whole thing has to be a little bit bigger to get the kind of torque you need for rotation braking. An alternative we saw a lot of other teams do at competition is really just a servo, a off-the-shelf geared down servo for the whole drum. And again, a lot of teams had a lot of success with that, but it was very slow. And then again, you have to sort of roll it back up.
Can you, when you get to the end of the rope, can you just let the spool go? Can you drop the spool with the rope? Is that legal?
So, I think the competition is that
it actually is legal to do that. The only I think condition on that is that as long as the rope doesn't fly away, but I mean it could be pretty easily solved with weights.
So I kind of like the rotary thing because you could do a centrifugal clutch on it that's just passive, so you don't have to control it. You'd have to tune it, but it would be self-limiting. Or some things are governed by basically have it run a fan, right? And the fan controls the speed. But I don't know if it's a kilogram. You might, depending on how you're gearing, you might need a bit of room for that bit of work. But again, it's once you got it, it's passive, and it would. But again, you have to release it at the end.
Yeah.
So with the release, also with the rope being attached to the central cylinder of the quick loop, maybe you could have a little rigid pin, which is just what it when it spins off, just falls down. It can solve the problem with the loose.
Yeah, just make sure you got a few turns when it lands, and then let it.
But I also want to satisfy all these suggestions. I can see where you're going with getting stoked on your perfect design and then prototyping it. So whatever works. So I'm all down.
So our most recent one, we attached this all to an RC receiver and transmitter, and we were able to. So the spring that we actually used in our prototype was much weaker than something that we're actually going to use. And so we actually managed to get the binary, it was able to hold the 1 kilogram rope, and basically, I would say 2 degrees on the throttle later, it was a full release, and that was about a 20 micron, no, it would have been about 40 micron resolution there on the throttle. And that was with the weaker spring and with acrylic. So I think the potential is there. We have the binary at the moment, and so kind of testing and tuning it that way.
If you really want to drop the fast, you can always try and basically free fall let it drop for most of the way, and then just veer slow down at the last minute.
That's the goal. We're going for this.
Yeah, I think. Yeah. No, yeah, rotary was something, just because we've tried it in the past, was something that we kind of steered away from because we already decided that we've made generations of prototypes that have yet to work. And this one worked straight off the bat, that it was able to hold it. And so that's kind of why we started going down this route, a little bit more of the rotary route. But in terms of perfecting this or taking the friction idea further, rotary might be something to consider.
I do have one question for you guys as well. So I think as a team, one thing that we definitely did focus on is, as Emily pointed out, was that make it work make it work first, get it working perfectly later. Mentality. Obviously, in certain applications in industry, for example, for an aircraft, that doesn't really work as well. But I don't want to try it that way. But anyways. Point being, what in industry, what would sort of be some of your thoughts on that sort of design mentality? Would you think that might have been the right approach as well going for these projects, or do you think maybe it would have been better to spend? Because I think it does come with a couple of pros and cons. Is that one thing is that once you get that thing that's working, then you sort of end up a little bit on the path towards fixation, right? But at the same time, you don't want to spend too much time considering all the options if you're only going to end up picking one. So I was wondering if you guys might have any thoughts on that.
It's always a balance, and it varies every time. Depends on how well can you model things, how well you know the technology you're dealing with, what's the cost of prototyping, what's the cost of simulation. I personally like to, fail early and fail often, right? That approach, because you learn a lot, and then you will often learn things very early on, and then focus on refining. The trap can be that if you do something too quick and too crude, you get a bad result, and you throw out maybe a good design. So it's a balance. I think, given the constraints you have, yeah, it's a good approach. What do you feel comfortable with? Try something that works, okay, go with that and refine it. It's not the approach I would have chosen, but you've gone through the pain of these other systems, and it's novel and it's exciting. Yeah, it varies from project to project, industry to industry, but I think a lot of people fail by going too far the other way, where they just analyze it to death, and then they go to build it and they find some fatal flaw. I think you just decided I don't see it. It kind of depends on how well understood the problem is and how much you can predict versus just need to try it. Just trying that out.
From my perspective, the building stuff and just seeing it come together is probably my favorite part. So the more I can spend away from the math and spend building it, as a student and being in a team in my spare time, that's my priority and that's what I enjoy the most.
Sometimes the team is just the thing that's going to get done, right? But it's the difference between getting done and not getting done too.
Yeah.
So on the pad, I'd say a couple of things. I like the idea of the rounded edges or something that's conforms a bit. I'd love to see that's a sort of old school die design, right? With the 4 posts.
Yeah.
Oh, it's over constrained, it's busy, can you simplify that with lecture probably, but again, at this point, if it works, it works. For material, I would look at urethane. Like urethane you can get in a whole range of geometers. It's really, really robust, great for wear, and you can just experiment with different geometers to find that balance of friction and wear capabilities.
Yeah.
I got some samples I can show you tomorrow.
Really cool.
See what I mean. Yeah. I guess kind of similar to your know that you have a bunch of like UHNW students, so like you had to kind of put on that fresh one.
Yeah.
Yeah, so you used to take one off and put one on the sometimes.
Yeah, I think in one of our iterations, we actually put the electrical tape on one of the acrylic patches to see what would happen. It was better, but not much. But definitely wanna. So like that's the other thing with this is that you can slide the pads off really easily and swap them out. So the spring is actually not fixed to the pads. So these are completely replaceable. We can have a series of pads glued to the sliding plate. So.
And your rover there, I would, since you're not worried about drag, like I would certainly exploit a truss structure under there, right? For the,
like,
yeah, from the bottom of the bottle up to that.
Right.
Up to the vertical web near the wheel.
Sure.
You can do some really nice trusses in there, make it really lightweight and nice and rigid. And it could be. You said plywood. You're making practical plywood.
Yeah, 1/8" plywood, just because it's accessible. I actually did consider carbon fiber plate and just cutting that. But I don't know. It seemed as though the carbon fiber was actually heavier than this, and we don't care as much about strength. So willing to sacrifice the strength for it. And we only had 3mm carbon fiber available to us from a source that we can afford. So basically it was 3mm carbon fiber or 1/8" plywood.
Oh, not wood. I mean, wood. The stiffness to the weight ratio of wood is excellent. Carbon fiber balance. This is kind of next to something that you already said you. Sorry, I didn't interrupt. No. I've kind of just been throwing this in the back of my head, but I was wondering if there's some way that you could optimize a little bit by attempting to use the wheel as a spool. And then have the rover lower itself using its wheel as a spool. And then you save weight on your overall by losing one mechanism. Maybe that's taking a little bit too complicated. I need to play with. It's so easy for like it.
Sounds fun.
That's the flair we were talking about.
Yeah.
Yeah, it's so crazy, it just might work. Use bottles. Use the bottle. Yeah.
Yeah.
You have to remember the bottle. So great pitch pushes against the bottle. Sorry, go ahead. You said you could mold tires with TP.
So
what's it? What's the geometry of it? Like
I have no idea. One of the team members has a printer that TP filament, and we just kind of.
Yeah. But it's a lot softer than.
It's soft, but I think the geometry is fairly high, but I think that it's not has a very low friction. That's my interpretation from just touching it, but.
Well, yeah, for another project, TPU tracks were printed to build like a little tank. However, without adding like material to generate more surface area, the track was rather slippery. on smooth surfaces.
It was, yeah.
Yeah, so we had to add a lot of like bumps to increase surface area to maximize that grip.
Yeah, I was gonna say you could put slots and tracks on it, and then give it some.
Yeah.
Some friction.
Yeah, the rubber bands, one of the issues that we're going into is that it's a little bit here. It's because it's just really hard to make it even and nicely spread. It's just not an even surface. It's a little bit wobbly. It's definitely, you can definitely work with it. But that was.
So what about O-rings?
O-rings. I haven't considered that yet.
Like you could, like if you got the softest geometer O-rings in, you can get EPDM or silicone maybe, and you could actually put, 2 or 3 of them wide.
Yeah.
But they would retain their thickness much better, right?
Yeah, and they would also look a bit nicer. Yeah, that could be something, and it's nice that we have like a nice even thing of it. It's like really easy to get hold of.
And you could put, like, it looks like you just had one. Can you go back to the next picture, the previous? Yeah. So you just got the one flange. You could put a flange on both sides.
Oh yeah.
And then you could just have like 2 or 3 O-rings across there.
Yeah. Yeah. Good idea. Yeah, we intend to like fasten this together mostly with glue just to save a little bit of weight on the fasteners. I'm personally a fan of the pieces because I feel like there's a lot more you can do with it. But this will probably be, we've got a lot more surface area here, so probably PVA type glue, but epoxy as well is super strong. And for a final prototype where it's not, we can take the time to make it nice and not messy everywhere.
Right, are there any final comments or questions as well? Thank you. Awesome. I guess, thanks everyone, UAS, for coming out, especially big thanks to Zaber and Adolin. Thank you guys for coming out. So I do apologize that we kept you a decent amount past what we promised, but having you guys' input is so key for us. This is actually the first time we've done an industry design review, but I think we've learned a lot over just this amount of time, and I think there's definitely a lot of things we can implement in both of our projects here. So I'm extremely grateful to have you guys here, and I think we can all say great big thank you to having you guys. I guess it was one more round of applause for that. So thank you. So I guess UAS people, you're free to go. If you guys want to stick around and talk, I know there were a lot of really cool, interesting conversations. Depends on if these guys are going to head out, but thanks everyone.